Okay, so it's already recording. The other day, the last 2 days that I was teaching the class, we were talking about tools for profiling applications at a large scale, but in the proprietary world. And we focus on a suite which is called Intel One API Toolkit, and that is focused on improving and profiling the performance of applications for Intel platforms. Today, we are going to do the same, but for the open source world. Okay, as you can imagine, Intel has its own tools, and probably they are the best suite of this kind in the proprietary world, but NVIDIA, for instance, that is the manufacturer of GPUs, has another tool which is called NVIDIA Insight, and also has optimized libraries like MKL, but in the case of NVIDIA, is divided or split into different mathematical libraries, like, for instance, QBLAS. Okay, AMD has something similar to BTune, but it's not so good. Actually, a few years ago, it didn't have anything, at least anything with interface, a visual interface, and now has something that resembles BTune, but is far from it. Okay, so I believe that Intel One API Toolkit is a good example of the kind of tools that you should find in the proprietary world. Today, as I told you, we are going to move to the open source world. You already know some of these tools from Emilio, for instance, Perf, Valgrind, etc. Okay, but it's worth to mention the set of tools that we are going to see in these 2 last classes of HPC tools that are the tools from the Barcelona Supercomputing Center. Okay, so they have a website, and if you go to this website, that is tools.bsc.es, okay, you are going to find like different tools that you can download and use in any cluster, in your own computer, or in a supercomputer. Okay, so we are going to explain this ecosystem because, as far as we know, in the open source world, this is the most complete suite of profiling tools available. Okay, focus on parallel programming and supercomputers. Okay, so let me put this in, okay, full screen. Sorry, not full screen, but presentation, yes, presentation mode. Okay, so we are going to see that, as it happened in the last tool from Intel Trace Analyzer and Collector, I don't know if you remember this tool that was intended to be used to analyze the performance of MPI application. It was actually divided into 2 different tools. The first one was intended to generate the trace during the execution of the application. In this case, we are going to have something similar, which is going to be called STRAE, okay? And then we have a tool, a separate tool, for visualizing the information of the trace. And in this case, the tool that we are going to use is Paraver, okay? You will see that many of these, okay, let me see. You will see that the name of many of these tools resembles Spanish words. Okay, so for instance, para ver in Spanish means to see, to watch. Okay, so you will see that many of these names have this kind of pattern. And then, using these tools, we are going to focus or cover separately two different use cases or study cases. The first one is applications, parallel applications that are parallelized for shared memory environments. Okay, and then we have parallel applications that are programmed using libraries for distributed memory environments. So this will be the case of OpenMP application, because this is what you are studying in parallel programming, and the other is MPI, okay, or any other library related to message passing and distributed memory programming. Okay, so the basic tool chain that we are going to use is Strive for generating the trace during the execution of the code, Paraver to analyze visually the performance of the application to detect hotspots and possible issues in the performance of the application. And there is an additional tool that is intended to compare our execution or our parallelization with an ideal one, okay? And this one is not going to be covered in this presentation, okay? Just the two of these. Strive to generate the trace, and after that, in a post-mortem analysis, we are going to use Paraver to visualize the trace, okay? DMMS is a nice tool, okay, but I believe that we have enough just covering the two previous tools. In this slide, you have the links that are relevant at this point. The website that I showed you before with the download links for the different tools. I told you that the most relevant are Strive and Paraver, and then the GitHub repository of the tools, okay? But it's not so important, the repository, because here you are going to find more up-to-date versions of the tools, but probably not so stable, okay? So for me, it's better if you just download the tools from the main website. Don't go to the GitHub repository. Okay, so as it happened with the One API Toolkit tools, the idea of these tools from the Barcelona Supercomputing Center is that you are going to profile your application first to detect what is going wrong, what is happening that is not working correctly, and after you do this analysis, you can optimize your code, focusing your efforts in those areas of the code where you consider that there is a problem, and there is a problem that you can that you have identified and that you are able to solve. Something that was also available in Intel Toolkit, but here is has a higher or a bigger emphasis, is the flexibility and versatility. Okay, so we are going to, these tools can be used in a number of platforms, Windows, Linux, etc., also in a number of hardware processors, environments, and for programs programmed using different programming models. Okay, in our examples, we are going to use always OpenMP and MPI, okay, but you will see that most of these tools are ready to analyze the performance of other kind of parallel programming libraries. Okay, so as I told you before, the first thing that we are going to use is Strive. The idea of Strive is that you can generate a trace with relevant events during the execution of the code, okay, to be later analyzed using the other tool, Paraver. Actually, the idea of the Barcelona Supercomputing Center and the development team of these tools is to decouple, okay, STRAE from Paraver. So even if you don't want to use Paraver, STRAE is a nice tool to generate a detailed log of events that are happening during the execution of a code, okay? And then you can analyze this log of events with Paraver, which will be easier, okay, because it's going to have many of the functionalities that you demand as a programmer, or you can create your own scripts to analyze the logs, like for instance, using Python scripts or things like this. It's going to work for different programming models, shared memory models such as OpenMP and pthreads. It's worth to mention at this point that it has supports for a programming model which is quite similar to OpenMP currently, and which is called OMPS. Okay, OMPS is the programming model created in Barcelona Supercomputing Center. Okay, it's quite similar to OpenMP, but it has its own syntax and its own runtime. And obviously, using the tools from Barcelona Supercomputing Center, you can analyze the performance of programs written using this technology. Also, it supports MPI for distributed memory environments, and also situations where you have hybrid programming. This means that you use MPI to distribute the work among different cores, and probably you are using OpenMP inside each node to parallelize the code in shared memory. Okay, so this is these are the environments and the things that are supported by STRAE. For instance, regarding programming model, it supports MPI, OpenMP, pthreads, OMPS, CUDA, OpenCL, Java, and Python. Okay, these two are languages. Regarding platforms, it supports mostly every platform that you can find, like Intel, Cray, BlueGene, ARM, Android, etc. It has support to extract the information of hardware counters, hardware performance counters, using the PAPI interface. Okay, when you are using perf in the open source world, you can extract the values of different hardware performance counters, such as, for instance, the number of level 2 cache misses, okay, or something like that. So you can do this also here. Let me see what is happening. Okay, somebody is asking for permission to enter. Now what? Admit. Okay, so using STRAE, you can generate information about these hardware performance counters during the execution of the code. It allows you to link the performance to the source code, and this was something that already happened in Intel One API Toolkit. Remember that when you have an issue in your application, normally you could identify in which parts of the source code was this issue, okay? So the same is going to happen in this case. Also, it has support, and it's usually the case, for periodic sampling. The idea of periodic sampling is that when you are generating a log of different events during the execution of a code, if you do that all the time, two things are going to happen. The first one is that the log is going to be huge. I mean, like several gigabytes of information per minute or something like that. And also that you are going to interfere a lot in the performance of the application because you are overloading the processor. Okay, so to avoid this, it's usual to do some sampling. So the idea is that instead of being all the time recording the different events that you want to record, okay, what you are going to do is to do it from time to time with a given frequency. And then you are going to try to infer the values for the other moments where you are not recording this information. Okay, so this is going to this is a kind of statistical approach to trace generation, but this is usually the case in the BSC tools, and it was also the case in the case of the Intel Toolkit. Also, you can use an API, a special API from Stripe that allows you to create user events. If you want to create your own events based on what is happening in the code, this is something that you can do. And the most important feature of this is that you don't need to recompile or relink the code against another library, okay? We will see how you are able to compile the code, and once you have your code compiled, using different approaches, you are going to be able to run it while generating the trace. Okay, so how this works, actually. There are three different alternatives. The first alternative is the one that we are going to use, and is the one that everybody will use, and is a feature that is used by many libraries, and is LD preload. Okay, so when you compile an OpenMP code with GCC or with ICC, you usually do something like GCC dash OpenMP. Okay, and this is going to do a couple of things. The first thing is to compile your code, the user code, but also is going to link, in this case, dynamically, and I'm not going to explain a lot about this, the OpenMP runtime with your program, okay? Because obviously, when you put a pragma, what is going to happen is that when you compile the code, it's going to insert calls to different functions of the OpenMP runtime to generate the parallel magic, to create the threads, spawn the threads, and to assign different parts of the work to different threads, okay? So when you do this something, using something that is called dynamic linking. And the idea of dynamic linking is that your binary, the binary code that is generated, is not going to contain the OpenMP runtime. It's going to just contain reference to the OpenMP runtime, okay? So every time you need to execute something of the OpenMP runtime, you are going to go to the OpenMP library code, and you are going to execute the corresponding part of this code. So this creates an opportunity to change this library at runtime. So the idea of Stripe is that they are going to replace leaf OpenMP, the library of OpenMP, by a version which is instrumented, okay, and that will be something like leaf OpenMP Stripe, that basically makes the trace generation, and at some point is going to make a call to the corresponding OpenMP library. Okay, so this is called symbol substitution through LD preload. This is the method. And this works not only with OpenMP, but also with MPI, with codes written with MPI and OpenMP, etc. Okay? Also, we have another alternative. This is not recommended, and is dynamic instrumentation. In the case of dynamic instrumentation, you are going to rewrite in memory the binary code. Okay, this is the binary code with the machine code that compose your application, and this this method, what it does is to insert trace generation code at certain points of the binary code. Okay, so this way you create another version of the binary which is instrumented to generate a trace of the execution during the execution of the code. And the last method is the most intrusive because it requires to recompile your application, and is, instead of doing this LD preloading thing, you are going to static linking your code against the OpenMP library, but with the Stripe code. Okay, so in the previous situation, you have a binary code with calls to different functions of the OpenMP library, and the binary code doesn't contain the OpenMP code, okay, the code of the OpenMP runtime. However, with static compiling, you have user code, and in the same binary, you are going to have the OpenMP code. This is what is called static linking, unlike the previous approach that was called dynamic linking. So when you do so, you need to use the OpenMP library with Stripe support, because you need to instruct OpenMP to generate traces during the execution of the program. Okay, so this is basically how it works in the underlying. Okay, it's not so relevant, but I believe that it's important that you understand how this works. So the idea is that with Stripe, using normally this code, this method, the one of LD preloading, you are going to generate a trace of the execution. And this is going to be one file or several files with lots of raw information. If you open one of these files, you are not going to understand anything, okay? Because it's just information that has to be processed by a machine, okay, somehow. So the tool to use in this case is Paraver. Paraver is intended to be used post-mortem. So in profiling, post-mortem means that you don't profile the application while it's being executed, but you execute it first, and once it's finished, then you are going to use the trace to analyze the information. And there is another possibility, which is called paramedir. As I told you before, these are names that resemble Spanish. Paramedir means to measure. Okay? So this is the meaning of the name of the tool. And the idea of paramedir is that it's a batch version of Paraver. So this means that if you want to do many different analyses and in an automatic way, okay, and you don't want an interface, a visual interface to make this analysis, then you can use paramedir instead of Paraver. I never use paramedir, okay? For me, for instance, Paraver is fine to analyze your code, as you will see later. Okay, so This is an example of the steps that you have to do to generate a trace during the execution of your program. Once you have installed Stripe in your own system, you are supposed to make a source of an SH file to do the configuration of Stripe. Remember that the same happened with Intel One API Toolkit. The first thing that you have to do in order to activate it was to source a file with the configuration. The same applies here. Then you have to use a configuration file which has an XML format and an XML extension in order to tell Stripe which kind of events you want to record in your trace. Okay? You want to record cache misses, you want to record OpenMP calls, MPI calls, whatever. Okay? This is going to be specified using a configuration file. We have a number of configuration files available for different use cases, so don't worry about this. There are like several examples, and different examples of these files are suitable for different scenarios. Okay, so you don't have to do anything new. And then you have to make the LD preloading. Okay, the idea of the LD preloading is that you are going to export this environment variable LD preload, and you are going to point this variable to the library that you want to put in the middle between your program and OpenMP or your program and MPI, just to include the code for the trace generation. And after you have done so, you are ready to go. You execute your binary with the same parameters that you will do it in any other case, and this is going to generate all the trace information. Okay? Okay, so there are a number of things that are new here. The first one is the library that we are going to load with LD preloading to put between your code and OpenMP or your code and MPI. And you can see in this table that depending on your program, you have to put different libraries. For instance, if your program is serial, it's not parallelized, this is the one that you have to preload. Leave, sec, trace. Okay? If your program is written just using MPI, you are supposed to put this one, leave, MPI, trace. Okay? If you are if your library, if your program use OpenMP, you're supposed to put this one, okay? And so on. You can see that depending on the parallelization technologies that you are using, you are going to put different versions of the same library. And even you have special cases for situations where you are using different parallelization technologies at the same time. For instance, this is a quite usual scenario. Sometimes you have a program that uses MPI and OpenMP at the same time. In that case, you are supposed to use these libraries. And as you can see, if you add the suffix F, this is going to give you Fortran support. Okay? By default, this is for C and C++. If you are using Fortran, you have to add an F at the end of the name of the library. The other component that we have to clarify from the previous set of steps to follow to generate the trace using Stripe is the configuration file. okay? When you install Stripe in your own machine, this is going to create several folders in your hard drive, and in one of them, you are going to find several XML configuration files for Stripe, which are applicable to different scenarios. For instance, in this folder, this configuration file is ready to trace information during the execution of a program which combines OpenMP and MPI, okay? If you have a program with just MPI, this is the configuration file that you should use at first, and for OpenMP, this is the configuration file that you should use at first. This is something that you can modify. I mean, you can make a copy of one of these configuration files and change several things in it. For instance, this is an example of what you are going to find in a configuration file. The first section, this is XML. It's a test format for configuration files and other things. So this enables the support for MPI, and for the MPI program, is going to record the value of different hardware counters. It also enables the support for OpenMP. It doesn't enable the support for log analysis, but it enables the support for counters, okay, and so on. You can see that it's quite straightforward to understand which is the meaning of the different sections of the configuration file and to create your own configuration file for your own purposes. An important section of this is the section where you identify the hardware counters that you are recording during the execution of your program. I don't know if you saw with Emilio hardware counters with perf, like the total number of instructions, total number of cycles, IPC, CPI, I guess you did, okay? Yes, okay, so the idea here is that you can put here a list of the hardware counters that you want to record during the execution of your application, okay? I believe that the maximum number of hardware counters that you can specify is 5, okay? So if you want to change it, you have to remove at least one to put a different one, okay? Probably this number of hardware counters is some kind of magic number, because if you record more counters at the same time, probably this can generate a big overload. Or maybe they thought that 5 counters was big enough. Also, during the generation of the trace, as you can imagine, the trace file is a file. So when you write information in the file, you are going to make a write in the hard drive. And this, obviously, as you remember by high-performance architecture, is very costly, okay? So instead of being all the time writing information to the file, you create like a buffer in memory, and once this buffer is full with information, the information is going to be copied or updated in the file. If you do this very often, okay, obviously this is going to degrade the performance of the application. So if you change this buffer size to a very small value, probably this is going to create a big overhead during the execution of the application. If you increase this value too much, probably you are going to have too much information from the trace generation in the main memory, and this is not usually a good idea. Also, you can enable sampling, as I told you before, and this is the period with which the events are going to be recorded. Okay, I believe this time is in milliseconds. Every 50 milliseconds, you are going to make this recording. And also, you can specify if you want the output in a single file or you want to combine it in if you want the output split it in different files, or if you want to merge them into a single one. Okay, so you run your application, and after you have configured everything, and once you finish, this is going to generate 3 different traces, okay? Trace files, PCB, PRB, and RAW. I'm not going to tell you about the format of this because this is going to be transparent to us, but the important thing for us is that the PRB file is the one that is going to be open later with Parallel, okay? That is the use that we are going to give to the Parallel, to the trace generated with Stripe. Okay. Now we are going to talk for a while about performance analysis with Parallel. Okay, so we have generated the trace during the execution of our code. We have the trace and we want to inspect it. Okay, we are going to make a small break because it's killing me my throat right now. So I'm going to make a break of, yes, I'm going to make a break of half an hour, okay, 30 minutes. And during this time, you can try to download Stripe in your own computer and start with the installation, okay? So I believe that with Emilio, you saw AutoTools or CMake? CMake. Okay, this has to be compiled with AutoTools, okay? That is a different tool. You can try it, okay? After that, we will continue with the class. Okay, I need to go to the bathroom right now. Okay, any questions in Teams? Okay, so, okay, let me, we will come back at, okay, 5:30 p.m. During this time, you are supposed to try to download and install Stripe in your own computer. Okay? I leave you here the link to the website. And also, if you are able to install it successfully, okay, you can try to run a code. For instance, one of your practice from parallel programming and try to generate a trace from it, okay? And later, after that, we will devote some time to talk about how to watch or to examine this trace using Parallel. Okay, so see you later.